Right now, while you're watching this, there's a sunspot aimed directly at Earth that's 10 times wider than our entire planet. Scientists are comparing it to the monster that triggered the most powerful solar storm in recorded human history, the one that caused telegraph equipment to spark and catch fire back in 1859. But here's what should genuinely unsettle you. While neighbouring regions have been exploding with fury, launching X-class flares that knocked out radio communications across entire continents, this giant AR4294 has been relatively quiet compared to its size and complexity, though it has produced some M-class flares and even an X1.1 flare on December 8th. And that silence? That's not reassuring. That's terrifying, because when a sunspot this massive, this magnetically complex, goes quiet after reaching Earth-facing position, it means all the energy is building up beneath the surface, coiling tighter and tighter like a spring that's about to snap. We've rarely seen a sunspot of this size and complexity appearing this late in the solar cycle, and right now we're staring directly down the barrel. Stay with me, we're going to understand exactly what's happening on our sun right now, why the silence from this monster is more dangerous than any explosion we've seen this year, what it would mean if it erupts while facing us, and why our entire technological civilization might be more fragile than you ever imagined. This isn't science fiction. This is happening right now, and by the end you'll understand why some scientists are watching their monitors with a kind of quiet dread they don't usually talk about in press releases. Let me paint you a picture of scale first, because numbers alone don't capture what we're dealing with. When astronomers say AR4294 is 10 times wider than Earth, they're talking about a magnetic structure so vast that you could line up 10 Earths side by side across its diameter, and still not span it completely. Imagine standing on our planet and looking up at something that makes our entire world look like a marble. That's what we're dealing with. This isn't some small dark freckle on the sun's face. This is a churning, twisting magnetic vortex larger than anything most of us can properly visualize, and it's rotating into perfect firing position. The geometry matters here. When a sunspot faces Earth directly, any explosion it produces, any coronal mass ejection it launches, comes straight at us like a bullet. There's no glancing blow, no deflection, just direct impact. But size alone doesn't tell the whole story. What makes AR4294 genuinely unprecedented is its magnetic classification. Solar physicists use a system to categorize sunspots based on their magnetic complexity, and it goes like this. Alpha regions are simple, bipolar magnets like the north and south poles of a bar magnet. Beta regions are more complex, with multiple spots of opposite polarity grouped together. Then you get beta-gamma configurations, where opposite magnetic polarities get so close together and so twisted that the field lines start intersecting in dangerous ways. And then, at the top of the danger scale, you get delta classifications. That's when opposite magnetic polarities aren't just close, they're sharing the same penumbra, the same outer structure. They're crushed together in a single magnetic pressure cooker. AR4294 is classified as beta-gamma delta. Let me translate what that means in practical terms. It means this sunspot has magnetic field lines that are twisted, compressed, and stressed to the point where they're basically a loaded weapon. The energy stored in those tortured magnetic structures is enormous, and the physics of magnetic reconnection, the process that releases that energy, doesn't ask permission. It happens when the tension becomes too great, when those twisted field lines snap back into simpler configurations and release all that stored energy in one catastrophic instant. We're talking about energy releases equivalent to billions of nuclear weapons, all focused into a single explosive event that can hurl billions of tons of magnetized plasma into space at speeds exceeding 1,000,000 miles per hour. And here's the thing that keeps solar physicists awake at night. Beta-gamma delta regions produce X-class flares, the most powerful classification we have, with frightening regularity. Statistically, a sunspot with this configuration has a significant probability, often around 20 to 30% per day, of producing a major eruption. The models say it should have already happened, but it hasn't. And that's the paradox that defines this entire situation. While AR4294 has been rotating across the sun's disk, moving into Earth-facing position day by day, it's been remarkably unusually quiet. Oh, there's been some activity, minor M-class flares. The kind of solar burps that happen regularly and don't threaten much beyond some radio interference, but nothing proportional to its size and magnetic complexity. Nothing that would relieve the building pressure. And meanwhile, just to the northeast of AR4294, another active region, AR4299, has been going absolutely berserk. X-class flares, multiple coronal mass ejections, Earth-directed plasma clouds that triggered geomagnetic storm watches and aurora displays. That region has been doing exactly what solar physicists expected a complex region to do, erupting with the kind of fury that makes headlines and fills space weather reports with warnings. But AR4294, silent, watching, building. And that contrast, that behavioral anomaly, is what has the attention of everyone who monitors our star professionally. Because here's what you need to understand about solar eruptions. They're not random. They follow patterns based on magnetic energy accumulation and release. When a region builds up magnetic stress, it either releases it through frequent smaller eruptions like a pressure valve letting off steam gradually, or it holds that stress until something triggers a massive, catastrophic release. AR4294 is doing the latter. Every day it doesn't erupt. Every rotation that passes without that magnetic snap adds more energy to the equation. The spring coils tighter, the rubber band stretches further, and physics tells us there's a limit to how much stress those magnetic structures can hold before they break. Think of it like this. Imagine a massive thunderstorm building overhead, clouds piling higher and higher, the air getting thick and electric. That feeling before lightning strikes when every hair on your body wants to stand up. But instead of thunder and lightning, there's just silence, just waiting. That's AR4294 right now. All the conditions are there, all the energy is building, but the discharge hasn't happened yet, and the longer it waits, the more energy accumulates, the bigger the eventual explosion could be. Solar physicists don't have a precise equation that tells them exactly when a sunspot will erupt, but they know the patterns, they understand the physics, and right now, those patterns are suggesting we're living on borrowed time. Every hour that AR4294 remains pointed at Earth without erupting is another hour of potential energy building up, another increment added to what could be coming. And here's what makes this moment different from every other solar threat you might have heard about and then forgotten. AR4294 appeared unusually late in the cycle. We're deep into solar cycle 25 right now, the sun's roughly 11-year pattern of increasing and decreasing activity, and we've already passed the expected peak. Activity should be declining. We should be seeing fewer large regions, not more. But AR4294 emerged anyway, defying the usual patterns, a late-cycle monster that has some solar physicists quietly wondering if something about this solar cycle is behaving differently than the models predicted. Solar forecasting is sophisticated, backed by decades of observation and increasingly powerful computational models, but it's not perfect. The sun is a massive ball of plasma with internal dynamics we can't directly observe, dynamo processes happening deep in its interior that generate these magnetic fields in ways we're still working to fully understand. When something unexpected happens, when a region like AR4294 appears when and where it shouldn't, it raises questions about what else we might not be seeing coming. The spacecraft watching AR4294 right now are humanity's early warning system. The Solar Dynamics Observatory, a NASA mission that's been staring at the sun continuously since 2010, captures images of AR4294 every few seconds in multiple wavelengths, watching for any sign of instability, any brightening or magnetic shearing that might indicate an eruption is imminent. The Solar and Heliospheric Observatory, positioned at a gravitationally stable point between Earth and the Sun, watches for coronal mass ejections, those massive plasma clouds that can take days to reach us but carry the real destructive punch of a solar storm. And ground-based observatories around the world are contributing their data, tracking the sunspot's magnetic evolution, measuring the field strength and complexity, trying to read the warning signs before the explosion happens. Because if AR4294 does erupt, if it launches a massive X-class flare and coronal mass ejection, while pointed directly at us, we'll have somewhere between 8 minutes and 3 days of warning, depending on whether we're talking about the light and radiation from the flare itself or the plasma cloud that follows. 8 minutes for the flare radiation to reach us. 1 to 3 days for the coronal mass ejection to cross the 93 million miles between Sun and Earth. That might sound like plenty of warning, and in some ways it is. Satellite operators can put their spacecraft into safe mode, power companies can adjust grid operations to handle the incoming stress, airlines can reroute polar flights to avoid radiation exposure. But here's the reality that should concern you. We've never actually experienced or fully stress-tested our modern infrastructure against a Carrington-class event, against the kind of solar storm that AR4294 is theoretically capable of producing if all that building energy releases at once in our direction. We have models, we have simulations, we have historical data from smaller storms, but we don't have certainty. And uncertainty, when you're talking about the infrastructure that powers everything from hospitals to water treatment plants to the internet, is not a comfortable place to be. So that's where we are right now, in this moment, while you're watching this video. A sunspot 10 times wider than Earth, magnetically complex enough to produce a civilization-threatening solar storm, is pointed directly at us, holding its fire, building energy, waiting for some trigger we can't predict. And we're watching it, monitoring every twist in its magnetic field, every flicker of activity, wondering if this will be the rotation that passes quietly or the rotation that changes everything. By the time you finish watching this video, AR4294 will have rotated a little further across the sun's face, either moving closer to the perfect firing angle or beginning its rotation toward the sun's western limb where any eruption would miss us. We're in the window right now. This is the moment when it matters most. And if you want to follow this story, if you want to know what happens next, hit that subscribe button and turn on notifications, because solar storms don't follow YouTube upload schedules, and if AR4294 erupts, you'll want to know about it immediately. Drop a comment telling me if you've been following this sunspot, or if this is the first time you're hearing about it, because I'm genuinely curious how many people realize we're living through one of the most significant space weather events in modern observation. Now let's understand why this matters so much, and to do that, we need to talk about what's been happening in AR4294's neighborhood while it sits quietly, because the context makes the paradox even more stark. While AR4294 has been sitting quietly, gathering strength, the solar region just northeast of it has been putting on a violent show that should have been our main concern if not for the silent giant next door. AR4299, a complex active region in its own right, erupted in early December with an X1.9 class solar flare that lit up space weather monitoring stations around the world and sent solar physicists scrambling to their models. X-class flares are the top tier of solar eruptions, the category reserved for the most powerful explosions our star can produce, and they don't happen quietly. The X-ray flux from that eruption flooded Earth's upper atmosphere, causing immediate radio blackouts across Australia and Southeast Asia, a sudden cascade of communications failures as high-frequency radio waves got absorbed by the suddenly ionized atmosphere before they could bounce back to Earth's surface. If you were flying over the Pacific that day, if you were on a ship in that part of the world relying on radio communications, you experienced minutes to hours of total silence, your signals swallowed by the sun's interference, but the flare itself was just the opening act. What came next was more concerning, more potentially dangerous, and it's what has everyone watching AR4294 with such intensity now, because it demonstrated exactly what these regions are capable of when they finally release their stored energy. On December 1st, AR4299 produced an X1.9 flare with an associated coronal mass ejection. Then, on December 6th at 2039 UTC, the region produced an M8.1 flare that launched another coronal mass ejection, a billion-ton cloud of magnetized plasma hurled into space at speeds approaching 1,000,000 miles per hour, and the trajectory analysis showed it was at least partially Earth-directed. Not a perfect bullseye, but close enough that the Space Weather Prediction Center issued a G3, strong geomagnetic storm watch for Earth. G3 storms are the third highest category in the 5-level geomagnetic storm scale, strong enough to cause voltage irregularities in power systems, strong enough to drag satellites in low Earth orbit down a little faster through increased atmospheric drag, strong enough to damage satellite components through deep charging effects, and absolutely strong enough to produce spectacular aurora displays visible at much lower latitudes than usual. And it delivered. When that coronal mass ejection arrived at Earth a few days later, the planet's magnetosphere, that protective magnetic bubble that shields us from most solar wind, got hammered. The sudden compression and twisting of Earth's magnetic field lines sent geomagnetically induced currents rippling through the ground, through the conductive rock and soil, and more importantly, through any long conductor that happened to be there, like power transmission lines, like pipelines, like railway tracks. Most power systems handled it without major disruption, but that's because G3 storms are within the range of what modern grids are designed to weather. They're not comfortable, they're not without effects, but they're survivable. What keeps engineers awake is thinking about what happens when you multiply that stress by a factor of 10 or more. When you get not a G3 storm, but a G5 extreme storm, the kind that hasn't hit Earth directly since the Halloween storms of 2003, or the more recent May 2024 event that pushed aurora down to the southern United States and caused satellite navigation issues. But here's what makes the AR4299 activity so relevant to understanding the AR4294 threat. These regions are neighbours on the solar surface, separated by only a small angular distance, and they're part of the same active region complex, meaning they likely share some common magnetic ancestry, some connection to the deep dynamo processes generating these fields. When AR4299 erupted, it demonstrated that the solar conditions right now, in this area of the Sun, in this period of the solar cycle, are conducive to major eruptions. The magnetic environment is unstable, the energy is there, the trigger mechanisms are active, and AR4294, which is larger and more magnetically complex than AR4299 was when it erupted, has been watching all of this happen while storing its own energy. It's like watching one powder keg explode and then turning to see a much larger powder keg sitting right next to it, fuse already lit, just waiting for the flame to reach the charge. The flares from AR4299 continued over several days. The region produced an X1.9 flare on December 1st, followed by an M8.1 flare on December 6th that launched an Earth-directed CME, prompting a G3 geomagnetic stormwatch for December 9th, eruptions one class down but still significant. Still capable of causing radio blackouts and launching smaller coronal mass ejections. Each one was a reminder that this part of the Sun is active, unstable, dangerous, and each one made the silence from AR4294 more noticeable, more ominous. Solar physicists have access to sophisticated models that predict flare probability based on magnetic field measurements, based on region size and complexity, based on historical behavior of similar regions. Those models gave AR4294 a high probability of major eruption, the kind of probability you don't ignore, the kind that says this region should be doing what AR4299 is doing, maybe even more so given its greater size and complexity. But it's not. It's quiet. And in solar physics, just like in any complex system, when something behaves very differently from what the models predict, it means either the models are missing something important, or the system is preparing to behave in an unexpected way, and neither possibility is particularly comforting. Let me give you a sense of the timeline here, because timing matters enormously in space weather. When AR4299 launched its Earth-directed coronal mass ejection, forecasters had roughly 2 days to prepare before it arrived. 2 days to issue warnings, to alert power grid operators, to reposition satellites if necessary, to reroute flights that would cross polar regions where radiation exposure spikes during solar storms. That's the normal warning window for a coronal mass ejection, the time it takes for that plasma cloud to traverse the space between Sun and Earth at typical speeds. But the flare radiation? That arrives in 8 minutes at the speed of light. 8 minutes from explosion to impact, no warning time at all except for those monitoring spacecraft that can see the flare beginning and send alerts to Earth in near real time. So if AR4294 erupts now, while you're watching this, the radiation will hit Earth's atmosphere before you finish this video. The coronal mass ejection, if it launches one, would arrive sometime in the next couple of days, depending on its speed and magnetic configuration. And here's what makes this moment so precarious. AR4294 is rotating across the Sun's face right now on the Sun's roughly 27-day rotation period, moving from east to west as viewed from Earth. When it first emerged on the Sun's eastern limb days ago, any eruption would have been pointed away from us, safely directed into empty space on the other side of the solar system. But as it rotated, day by day, it moved closer to central solar meridian, that imaginary line running from solar north to solar south that divides the Earth-facing hemisphere. Right now, AR4294 is either at or very near that central meridian position, meaning any eruption is aimed almost directly at Earth. This is the Geoeffective window, the period when a solar eruption from this region would have maximum impact on our planet. And that window doesn't last forever. In a few more days, AR4294 will rotate past central meridian and begin moving toward the Sun's western limb, and any eruption would be pointed increasingly away from us, the impact geometry getting less and less direct until eventually it rotates onto the Sun's far side where we can't even see it anymore. So we have this narrow window, this handful of days, when AR4294's behavior matters most to Earth. And during this window, while AR4299 has been demonstrating what active regions in this solar neighborhood are capable of, AR4294 has maintained its ominous quiet. The magnetograms, the measurements of magnetic field strength and configuration on the solar surface, show that the region hasn't simplified. It hasn't released its stress, the delta configuration is still there, the energy is still building, and every hour that passes without eruption is another hour of accumulated stress, another increment of stored energy that will eventually find release one way or another. Physics demands it. Magnetic fields under stress seek lower energy states, and the path from stress to relaxed runs through reconnection events, through flares and eruptions, through the violent release of energy that we've been expecting and haven't yet seen. The Aurora chasers had their moment when AR4299's coronal mass ejection arrived. Social media filled with stunning photographs of green and purple curtains dancing across skies in Canada, the northern United States, northern Europe, places where Aurora are special but not unheard of. But those displays, beautiful as they were, came from a G3 storm. Now try to imagine what happens when you multiply that impact by a factor of 5 or more, when you're not dealing with a G3 storm but a G5 extreme event. The kind that pushes Aurora into the tropics, the kind that makes power grids scream under the electromagnetic assault, the kind that hasn't happened in the modern satellite era in its full fury. That's what AR4294 is theoretically capable of producing if everything goes wrong in exactly the right way, if the eruption is powerful enough, if the coronal mass ejection is fast enough and dense enough, and carries the right magnetic orientation, if the impact geometry is direct enough. All of those ifs have to align, and that's why most solar eruptions, even from complex regions, don't produce catastrophic effects. But some do. History tells us that unequivocally, and the physics tells us that AR4294 has all the ingredients. The radio blackouts from AR4299's activity were textbook demonstrations of how solar flares affect Earth even without a coronal mass ejection. The X-rays and extreme ultraviolet radiation from the flare hit Earth's upper atmosphere, the ionosphere, and dramatically increased the ionization level in the layer, the lowest part of the ionosphere. That enhanced layer absorption is deadly for high-frequency radio waves, which depend on bouncing off the higher layers of the ionosphere to propagate over long distances. When the layer gets supercharged by flare radiation, those radio waves get absorbed instead of reflected, and communications go dark. For most of us, that's invisible. We don't use HF radio in daily life. But for aviation, for maritime operations, for military communications, for emergency responders in remote areas, HF radio is critical infrastructure, and losing it even temporarily is a significant operational problem. Now scale that up. Imagine an X-class flare 5 times more powerful, 10 times more powerful. Imagine the blackout zone expanding, the duration extending, the recovery taking longer. That's part of what AR4294 could deliver if it erupts during its Earth-facing window. But even with all of AR4299's activity, even with the X-class flares and the coronal mass ejections and the geomagnetic storms and the radio blackouts, the forecasters were never truly worried in the way they're quietly worried now about AR4294. Because AR4299, for all its fury, wasn't in the same size and complexity class. It was dangerous, absolutely, but it was predictably dangerous, doing what active regions that size typically do. AR4294 is different. AR4294 is in a category that demands comparison to historical events, to the monsters of solar history that set benchmarks for destruction. And to understand what that means, to understand why scientists invoke names like Carrington when they talk about this sunspot, we need to go beneath the visible surface and understand what's actually happening in that magnetic cauldron. Why the structure of AR4294 makes it not just dangerous but potentially catastrophic, and why silence, in this context, amplifies rather than diminishes the threat. To understand why AR4294's silence is more threatening than AR4299's violence, you need to understand what's actually happening beneath that dark patch on the sun's surface, because sunspots aren't just cosmetic blemishes. They're windows into a magnetic hell, visible markers of processes happening deep inside the sun that we can only observe through their surface effects. The sun isn't a solid body, it's a massive ball of plasma, ionized gas where electrons have been stripped from atoms by sheer temperature, creating a medium that conducts electricity and generates magnetic fields through dynamo processes we're still working to fully map. Deep in the sun's interior, roughly a third of the way down from the surface, there's a boundary layer called the tachocline where the sun's rotation rate changes dramatically. Above this boundary, the outer convective zone rotates differentially, faster at the equator than at the poles. Below, the radiative interior rotates more like a solid body. That difference in rotation rates, stretches and twists magnetic field lines like someone wringing out a towel, amplifying small seed fields into the powerful magnetic structures that eventually rise to the surface and create sunspots. When those magnetic flux tubes break through the photosphere, the visible surface of the sun, they create the structures we call active regions. The magnetic field is so strong in these areas, thousands of times stronger than Earth's surface magnetic field, that it suppresses the convection that normally brings hot plasma up from below. Convection is what makes the sun bright, hot material rising and radiating energy before cooling and sinking back down. But in sunspot regions, the magnetic field acts like a plug, reducing convection, and that makes these areas cooler and darker than the surrounding photosphere. Still unimaginably hot by any terrestrial standard, around 4,000 degrees Celsius compared to the surrounding 6,000 degrees, but cool enough to appear dark by contrast. That's why sunspots are black when you see them through properly filtered telescopes. You're seeing areas where magnetic interference has reduced the temperature enough to make them noticeably darker than their surroundings. But the darkness is just a symptom. What matters is the magnetic structure, and in regions like AR4294, that structure is incredibly complex and stressed. The beta-gamma-delta classification I mentioned earlier isn't just labeling for convenience. It describes a specific and dangerous magnetic topology. In simple sunspot groups, you have a leading spot of one magnetic polarity and a trailing spot of opposite polarity, like the north and south poles of a magnet. The magnetic field lines arc through the corona connecting these opposite poles, and while these regions can certainly produce flares, the magnetic configuration is relatively stable. But as you add complexity, as you get multiple spots of different polarities crushed together in a small area, as you get opposite polarities sharing the same penumbra like in a delta configuration, you create conditions where magnetic field lines from opposite polarities are forced into extremely close proximity, twisted and sheared and compressed until they're on the edge of instability. Think of magnetic field lines like rubber bands stretched between 2 points. In a simple configuration, the rubber bands are stretched but not twisted. In a complex configuration, they're not just stretched but wrapped around each other, tangled, with multiple connection points and crossing paths. And just like twisted rubber bands store elastic energy that gets released when the rubber snaps back to a relaxed configuration, these twisted magnetic structures store enormous amounts of energy in the magnetic field itself. That energy density is what makes beta-gamma delta regions so dangerous. They're not just slightly more active than simpler regions. They're fundamentally different in their energy storage capacity and their potential for explosive release. The process that releases this energy is called magnetic reconnection, and it's one of the most important and violent processes in plasma physics. Here's how it works in simplified terms. When you have magnetic field lines of opposite polarity pressed very close together, there's a point where the mathematical idealization of infinitely thin field lines that never cross breaks down. In reality, in plasma with finite conductivity, those field lines can break and reconnect in a different configuration. Imagine taking two rubber bands stretched in opposite directions, cutting them at their crossing point, and then reconnecting the ends differently so the tension gets released. That's magnetic reconnection in a mechanical analogy. The field lines snap into a simpler, lower energy configuration, and all that stored magnetic energy gets converted almost instantaneously into other forms. Kinetic energy, accelerating plasma to a significant fraction of light speed, thermal energy heating plasma to tens of millions of degrees, and radiation across the entire electromagnetic spectrum from radio waves to X-rays. That's a solar flare. That's what happens when magnetic reconnection cuts loose in a complex active region. And in a beta-gamma delta region like AR4294, the amount of energy available for release is staggering because of how much magnetic stress has accumulated. The larger the region, the more magnetic flux, the more stored energy. The more complex the configuration, the more reconnection sites, the more potential triggers for that explosive release. And when a region this large, this complex, this stressed finally erupts, the scale of the eruption can be proportionally massive. X-class flares are classified on an open-ended scale, x1, x2, x5, x10, with each integer representing a doubling of peak X-ray flux. The most powerful flare in modern observation was an X28 event in 2003, though its peak flux was off the scale of instruments at the time. AR4294, given its size and complexity, could theoretically produce something in that range if conditions align. And that's before we even consider the coronal mass ejection that would likely accompany such an eruption. Because here's what many people don't realize. The flare and the coronal mass ejection are related but distinct phenomena. The flare is the radiation release, the electromagnetic pulse that travels at light speed and arrives at Earth in 8 minutes. It's dangerous to satellites, to radio communications, to anything in line of sight to the sun when it happens, but it's over in minutes to hours. The coronal mass ejection is the matter release, the billion-ton plasma cloud hurled into space by the same magnetic reconfiguration that produced the flare. That plasma is magnetized, carrying twisted field lines embedded in the cloud, and it travels much slower, typically a few hundred to maybe 2,000 kilometers per second in extreme cases. That's why it takes days to reach Earth. But when it arrives, when that magnetized plasma cloud slams into Earth's magnetosphere, that's when the real damage potential emerges for ground-based infrastructure, because the interaction between the CME's magnetic field and Earth's magnetic field creates those geomagnetically induced currents that can overload power grids and blow transformers. So a major eruption from AR4294 would be a two-stage threat. Stage 1 hits at light speed with radiation that can disable satellites, disrupt communications, and increase radiation exposure for astronauts and high-altitude aircraft. Stage 2 arrives days later with a massive coronal mass ejection that could trigger the kind of geomagnetic storm that brings down power grids. And right now, we're in the window where both stages would be aimed directly at us. The geometry is perfect for maximum impact. And yet, AR4294 isn't erupting. The magnetic stress is there. The magnetograms show it clearly. The delta configuration, the twisted field lines, the compressed opposites sharing space they shouldn't share, all of it visible in the data. The statistical models say eruption is likely. The comparison to historical events says eruption is expected, but it's not happening. And that brings us to the core of the paradox. Why hasn't AR4294 erupted yet? There are a few possibilities, none of them particularly comforting. One possibility is that the magnetic stress, while enormous, hasn't quite reached the critical threshold for reconnection to begin. Magnetic field lines can sustain tremendous stress before they break and reconnect, and maybe AR4294 is right at that edge, teetering on the brink but not quite over. Every passing hour adds more stress as the region continues to evolve, as subsurface flows continue to twist and shear the field lines, as new flux continues to emerge into the region. From this perspective, eruption isn't a matter of if but when, and the longer it waits, the more energy will release when it finally happens. Another possibility is that something about the magnetic configuration is temporarily stable in a way the models don't fully capture. Magnetic reconnection requires specific conditions, not just proximity of opposite polarities, but also the right plasma environment, the right triggering instability. Maybe AR4294's magnetic structure, for all its apparent stress, is in a temporarily stable equilibrium, a local energy minimum that requires a specific perturbation to trigger the cascade into full eruption. Like a ball balanced perfectly on top of a hill. The slightest push sends it rolling, but without that push, it could theoretically sit there for a while. But the sun isn't static. Convective flows beneath the surface are constantly changing. New flux is always emerging. External perturbations are inevitable. So even if AR4294 is in a temporarily stable state, that stability can't last indefinitely. A third possibility, the one that should genuinely concern us, is that AR4294 is building towards something larger than the statistical models predict. That the unusual silence is a precursor to an unusually powerful eruption, that we're watching a rare event unfold in real time and don't fully recognize it yet. Solar physics is built on statistics derived from limited observation time. We've been watching the sun closely for decades, which sounds like a lot until you remember the sun is billions of years old and operates on cycles that can span centuries or longer. Our observational record is a tiny slice of solar behavior, and while we understand the basic physics, we don't have perfect predictive power for individual events. Extreme events, by definition, are rare and poorly sampled. If AR4294 is preparing to do something genuinely exceptional, something that pushes the boundaries of what we've observed in the modern era, then its unusual behavior might be precisely because it's not following the usual patterns. It's exploring a different part of the possibility space, one we haven't seen enough times to recognize in advance, and that's the uncomfortable truth that sits beneath all the monitoring and modeling and forecasting. We're watching a complex nonlinear system with incomplete information, trying to predict something that happens on timescales, from seconds to days based on measurements and models that are sophisticated but not omniscient. We know AR4294 is dangerous. We know it has the potential for major eruption. We know the geometry is currently optimal for Earth impact. But we don't know when or if it will erupt during this rotation, and we don't know how powerful that eruption will be if it comes. We're watching and waiting, like someone staring at a coiled spring, knowing it's under tension, knowing it's going to snap eventually, but unable to predict the exact moment when the physics finally gives way and all that stored energy releases in one violent instant. And while we watch this magnetic spring coil tighter on the sun's surface, it's worth remembering that this isn't the first time humanity has found itself staring at a solar monster, wondering what would happen if it truly unleashed its fury. History has given us a preview, and the preview should terrify anyone who understands just how dependent our modern world has become on technologies that didn't exist the last time the sun really showed us what it could do. On the morning of September 1st, 1859, British astronomer Richard Carrington was doing what he did every clear day, projecting an image of the sun onto a screen in his private observatory and carefully sketching the sunspots he observed there. Carrington was a meticulous observer, one of the first to systematically track sunspots and recognize that they rotated with the sun's surface, and on that morning he was observing a particularly large and complex sunspot group. And then something extraordinary happened. Carrington watched as two brilliant beads of white light appeared in the sunspot group, intensely bright points that he'd never seen before in years of solar observation. He was witnessing a solar flare in white light, something so energetic that it was visible to the naked eye through his solar projection, and he knew instantly he was seeing something rare. He called for a witness, but by the time someone else arrived, the brightening had already faded, lasting only about 5 minutes. Carrington sketched what he'd seen and recorded the time, and then he waited to see if anything else would happen. He didn't have to wait long. 17 hours later, auroras erupted across Earth's skies with an intensity never seen before or since in recorded history. Witnesses across the Caribbean, Mexico, the American South, across Europe and Asia, saw green and red curtains of light filling the night sky, so bright that people could read newspapers by aurora light at midnight. In many places, people genuinely believed they were seeing the early dawn, and started their morning routines hours before actual sunrise. But far stranger and more disturbing than the pretty lights were the effects on the most advanced technology of the age, the telegraph system. Telegraph operators across Europe and North America reported that their systems had gone haywire. Sparks flew from telegraph equipment, shocking operators and setting papers on fire. Some operators disconnected their batteries entirely and found that the telegraph systems continued to work anyway, powered solely by the geomagnetically induced currents flowing through the wires, the phantom electricity generated by Earth's violently disturbed magnetic field. Messages could be sent across hundreds of miles with no electrical power source at all, except the aurora raging overhead. It was simultaneously fascinating and terrifying, a demonstration that something from the sun could reach down and manipulate human technology in ways no one had anticipated. That was the Carrington Event, the most powerful solar storm in modern recorded history, and the benchmark against which all subsequent space weather threats are measured. Carrington himself made the connection between what he'd observed on the sun and the aurora and telegraph disruptions that followed, publishing his observations and suggesting, controversially for the time, that events on the sun could directly affect Earth. He was right, of course, though the mechanism wouldn't be fully understood for another century. What Carrington had witnessed was a massive solar flare and coronal mass ejection from a sunspot group that launched billions of tons of magnetized plasma directly at Earth at exceptional speed. The transit time was unusually short, less than 18 hours compared to typical 2 to 3 day transits, suggesting the plasma cloud was moving at nearly 3,000 kilometers per second, extraordinarily fast even by CME standards. And when it hit Earth's magnetosphere, it triggered a geomagnetic storm so powerful that the auroral oval, normally confined to high latitudes, expanded all the way to the tropics. Now here's what should keep you awake at night. The telegraph system in 1859 was the extent of electrical infrastructure. There were no power grids, no satellites, no GPS, no internet, no cell phone networks, none of the technologies that define modern civilization. The Carrington Event damaged telegraphs because telegraphs were the only vulnerable technology that existed. Today, if a Carrington-class event happened, the list of vulnerable systems would be almost everything we depend on. And AR4294, by size and magnetic complexity, is comparable to the sunspot Carrington observed. We're looking at a modern Carrington candidate, and it's facing Earth right now. The size comparison is direct and unsettling. Carrington's sunspot group was visible to the naked eye, large enough to see without a telescope if you used proper solar filters. Historical records suggest it spanned an area at least 10 times the size of Earth. AR4294 matches that scale. It's not speculation or exaggeration to say this sunspot is in the same class as the one that produced the most powerful solar storm in recorded history. The magnetic complexity is there, the energy storage capacity is there. The only question is whether it will erupt during its Earth-facing passage, and whether that eruption will be as powerful and as well-aimed as Carrington's was. Those are not comfortable uncertainties to live with when you understand what a modern Carrington event would actually mean. Because here's the thing, most people don't fully grasp about space weather threats. The danger isn't really to you personally, not in a direct physical sense. You won't feel a solar storm. You won't see anything unusual unless you're lucky enough to catch the aurora. The radiation increase at ground level from even a major solar flare is negligible because Earth's atmosphere shields us beautifully. But our technology isn't shielded. Our infrastructure is vulnerable in ways that simply didn't exist in 1859. The very things that make modern civilization function, the electrical grids and satellite networks and communication systems, are precisely the systems that solar storms can disrupt or destroy. And unlike a hurricane or an earthquake, which affect a region, a Carrington-class solar storm affects an entire hemisphere. Everything facing the sun when the coronal mass ejection arrives, all at once, with no regard for national borders or disaster preparedness plans. Power grids are the critical vulnerability, the infrastructure that, if it fails, takes almost everything else with it. Modern grids are massive interconnected networks of generators and transformers, and thousands of miles of transmission lines, and those long transmission lines act like antennas for geomagnetically induced currents during a geomagnetic storm. The physics is straightforward. A geomagnetic storm is caused by the interaction between the CME's magnetic field and Earth's magnetosphere, which creates rapid variations in Earth's magnetic field at the surface. Faraday's law of electromagnetic induction tells us that a changing magnetic field generates an electric field, and if there's a conductor present like a power transmission line that can be hundreds of miles long, that electric field drives a current through the conductor. That's a geomagnetically induced current, and it flows into the power grid through the grounded neutrals of transformers, where it can cause serious problems. The high-voltage transformers that step power up for long-distance transmission and step it back down for distribution are designed to handle alternating current at 60 Hz in North America, or 50 Hz in most of the rest of the world. They're not designed to handle quasi-DC currents flowing through their windings, which is effectively what geomagnetically induced currents are. When these currents flow through a transformer, they cause what's called half-cycle saturation, where the transformer's magnetic core gets pushed into saturation on one half of the AC cycle. That generates harmonics, overheats the transformer, and can cause permanent damage. In extreme cases, transformers can fail catastrophically, burning out in minutes or hours under the stress of a major geomagnetic storm, And here's the nightmare scenario. These high-voltage transformers are not mass-produced. They're custom-built, often overseas, with manufacturing and delivery times measured in years. If a Carrington-class event damaged or destroyed hundreds of these transformers across a continent, replacing them would take years even under the best circumstances. And without transformers, you don't have a functioning power grid. Without a functioning power grid, modern civilization stops. Let me be very concrete about what that means. No power for days or weeks is an inconvenience, the kind of thing we experience after a major hurricane or ice storm. No power for months or years is a civilizational breakdown. Hospitals run on generators for a while, but generators need fuel, and fuel distribution requires powered pumps and refineries. Water treatment plants stop operating, which means no safe drinking water in most cities. Sewage systems fail. Food refrigeration fails, leading to massive spoilage. Supply chains break down because modern logistics depend entirely on electronic systems and GPS for coordination. Communication networks fail because cell towers and internet infrastructure need power. Banking stops because ATMs and electronic payment systems don't work. In short, everything that makes a city of millions livable stops functioning, and you can't evacuate millions of people from multiple cities simultaneously because the transportation systems also run on fuel and electronic coordination that wouldn't be available. This isn't science fiction disaster thinking. This is what infrastructure experts and emergency planners model when they think about worst-case space weather scenarios. And we know it's not just theoretical because we've seen glimpses of it, small-scale previews of what a major event would do. In March 1989, a solar storm substantially smaller than the Carrington event hit Earth and caused a cascading failure in Quebec's power grid that left 6 million people without power in 90 seconds. 90 seconds from storm arrival to blackout, because the geomagnetically induced currents overloaded key components and protective systems tripped in rapid succession. Quebec's grid was back online in 9 hours, but that was a much smaller storm and a much more limited failure. Scale that up to Carrington intensity, multiply the affected area by 10 or 100, and recovery time stops being hours and starts being measured in very different units. The Carrington event caused telegraph equipment to malfunction, spark, and in some cases catch fire, and created spectacular auroras. A modern Carrington event would do so much more damage precisely because we have so much more to damage. And the cruel irony is that our increasing technological sophistication has made us more vulnerable, not less, because we've built a civilization that depends absolutely on systems that are fragile in the face of space weather. We've created a single point of failure in the form of electrical infrastructure, and the sun has the demonstrated capability to attack that point of failure from 93 million miles away. That's the shadow the Carrington event casts over modern society. The knowledge that something that happened once can happen again, and next time, the consequences won't be damaged. Telegraphs and pretty lights, but potentially the breakdown of the systems that keep billions of people alive. And as we watch AR4294 rotate across the sun's face, we're forced to confront the possibility that we might be living through the early stages of the next Carrington event. That this could be the rotation that tests whether our modern infrastructure can survive what 1859-era telegraph systems barely weathered. But to really understand the full range of possibilities, to grasp just how much worse things could potentially get, we need to talk about why AR4294 appeared when it did, why the models didn't predict it, and what that tells us about the limits of our understanding of the star we depend on for everything. Solar cycle 25 wasn't supposed to be particularly remarkable. When the expert panels convened to make their predictions several years ago, analysing decades of solar observations and running sophisticated models of the solar dynamo, the consensus forecast was for a modest cycle, similar in intensity to the relatively weak solar cycle 24 that preceded it. The Sun follows an approximately 11-year cycle of magnetic activity, rising from solar minimum when the Sun is relatively quiet with few sunspots, up through solar maximum when active regions proliferate, and solar storms become frequent, and then declining back toward the next minimum. These cycles have been tracked systematically since the mid-1700s, and while no two cycles are identical, there are patterns, statistical regularities that allow forecasters to make educated predictions about what's coming. Solar cycle 25 was predicted to peak around 2025, with a smooth sunspot number reaching maybe 115 or so, putting it firmly in the category of modest activity. Not a monster cycle like solar cycle 19 in the 1950s that reached numbers near 200, but not a dead cycle either. A middle-of-the-road, unremarkable solar cycle that would come and go without exceptional drama. Except that's not what happened. Solar cycle 25 started stronger than predicted almost from the beginning, with sunspot numbers consistently exceeding the forecast values. The sun was more active than the models anticipated, producing more sunspots, more active regions, more flares than expected for this phase of the cycle. By 2024, it was clear that something was different, that either the sun was ramping up faster than predicted, or the peak would be higher than forecast, or both. The models, sophisticated as they are, were missing something about this cycle's behaviour, and then, in late 2025, well past the expected peak, after activity should have started its decline toward the next solar minimum, AR4294 appeared, a late-cycle monster, a massive complex active region emerging when and where the statistical pattern suggested it shouldn't. Now, to be clear, solar forecasting is hard. The sun is a ball of plasma heated to millions of degrees by nuclear fusion in its core, with complex fluid dynamics and electromagnetic processes happening throughout its interior and atmosphere. The magnetic fields that create sunspots are generated by dynamo action deep inside the sun, in regions we can't directly observe, through processes we understand in outline but not in every detail. Predicting exactly when and where a sunspot will emerge is beyond our current capabilities, but predicting the overall level of activity, the statistical likelihood of large regions during different phases of the cycle, that's something solar physics has gotten reasonably good at over decades of observation and modelling. So when the actual behaviour significantly exceeds predictions, when a region like AR4294 appears as an outlier to the expected patterns, it raises fundamental questions about what we're missing. Part of the challenge is that 11-year cycle isn't the only rhythm the sun follows. There are longer-term patterns, multi-decadal variations in solar behaviour that modulate the amplitude of the 11-year cycles. There's evidence from historical records and cosmogenic isotope data that the sun goes through extended periods of higher and lower activity on timescales of centuries. The Maunder minimum in the late 1600s was a period of severely depressed solar activity, almost no sunspots for decades, coinciding with the coldest part of the Little Ice Age. The modern maximum, roughly spanning the mid-20th century, was a period of generally elevated solar activity, with several very strong cycles in succession. These longer-term variations suggest there are processes in the solar interior, modulations of the basic dynamo mechanism, that we don't fully understand or predict. So when solar cycle 25 behaves differently than predicted, one possibility is that we're seeing the effects of some longer-term variation, some shift in the underlying dynamo that the short-term models don't capture. But there's another, more uncomfortable possibility. Maybe the models are missing something more fundamental about how the solar dynamo works, some nonlinear behavior or chaotic element that makes long-term prediction inherently limited. The solar dynamo is believed to operate at the tachocline, that boundary layer between the radiatively stable interior and the convectively unstable outer third of the sun. The differential rotation at that boundary stretches and amplifies magnetic fields through a process involving the twisting of field lines by convective motions, but the details are fiendishly complex. We can't observe the tachocline directly. We can infer its properties through heliosismology, measuring acoustic waves that propagate through the sun's interior and using those measurements to map internal structure and flows, but it's indirect information with significant uncertainties. If something about the dynamo process has shifted, if the sun has transitioned into a slightly different mode of operation, we might not recognize it immediately because our observational baseline is so limited in cosmic terms. Think about what we're attempting here. We're trying to predict the behavior of a massive magnetohydrodynamic system, using observations spanning a few decades to maybe a couple of centuries in detail. The sun is over 4.5 billion years old. Our detailed observational record is less than 1/1,000,000th of the sun's lifetime. We're like someone trying to predict the behavior of the ocean after watching waves for 3 seconds. Yes, you'd learn something about waves in those 3 seconds. You'd see patterns, you'd start to develop ideas about what causes waves and how they propagate, but you wouldn't see a tsunami, you wouldn't see a rogue wave. You wouldn't witness the full range of behaviors the ocean is capable of because you haven't watched long enough to catch the rare events. And rare events, by their nature, are the hardest to predict because we have the least data on them. AR4294's late-cycle emergence is anomalous enough that it's prompted some solar physicists to wonder if we're seeing a preview of something unusual, a hint that solar cycle 25 might not follow the standard pattern all the way to its conclusion. Most solar cycles are roughly symmetric, taking about 5 years to rise from minimum to maximum, and another 5 or 6 years to decline back to minimum. But there's variation. Some cycles have sharp peaks and gradual declines. Others have extended plateaus near maximum or secondary peaks. The detailed shape of the cycle depends on the underlying dynamo behavior, and if that behavior is different this time, the cycle shape might be different. It's possible that solar cycle 25 is entering an extended maximum phase, maintaining high activity longer than expected. It's possible that we're seeing a burst of late cycle activity before the decline truly begins, or it's possible that this is just statistical variation, that AR4294 is an outlier that would fit within the range of normal behavior if we had a longer observation baseline. We don't know. And that uncertainty, that acknowledgement that our models have limits and our predictions aren't perfect, is something the space weather community takes seriously but the public often doesn't hear about. The forecasts you see, the predictions for solar cycle behavior, come with uncertainty ranges, confidence intervals that acknowledge the models aren't perfect. But in public communication, those uncertainties often get lost, and we're left with a single forecast number as if it's gospel truth. Then when the sun doesn't cooperate, when it does something like produce AR4294 at an unexpected time with unexpected intensity, it can seem like the experts don't know what they're doing, but the reality is more nuanced. The experts know a great deal, but they also know the limits of that knowledge, and those limits are wider than many people assume. Here's what makes this particularly relevant to the AR4294 threat. If the models missed predicting this region's emergence, if the sun's behavior is deviating from expectations in ways we don't fully understand, then what else might the models be missing? Are the flare probability predictions as reliable as we think? Are the estimates of how powerful an eruption could be from a region this size and this complex based on solid statistics or extrapolations from limited data? When forecasters say there's a certain percentage chance of an eclipse flare from AR4294, those percentages come from historical correlations between region characteristics and flare production. But those correlations are based on the events we've observed, and if AR4294 is unusual in ways beyond just its size and timing, if it's exploring behavior space we haven't sampled thoroughly, then the statistical predictions might not be as reliable as we'd like. This isn't a failure of science. This is science operating at the edge of knowledge, making the best predictions possible with available data and models, while honestly acknowledging that surprises are possible when you're studying complex systems with limited observational history. But for those of us on Earth, watching AR4294 rotate into firing position, the practical consequence of that uncertainty is discomfort. We can't predict with certainty whether it will erupt. We can't predict how powerful an eruption would be if it happens. We can estimate, we can calculate probabilities, we can monitor for signs of instability, but we can't know for sure until it happens or doesn't happen. We're in a position of reactive rather than proactive capability. We can see the threat, we can watch it evolve, but we can't prevent it or predict it precisely enough to do more than prepare for possibilities. And there's a deeper layer to this uncertainty that touches on some genuinely unsettling physics. The sun's magnetic field doesn't just affect the photosphere where we see sunspots. It extends throughout the solar interior and out into the heliosphere, the bubble of solar wind and magnetic field that surrounds the entire solar system. The behavior of that global magnetic field, including how it flips polarity every 11 years during solar maximum, is connected to the dynamo processes in the solar interior. If something about the dynamo is changing, if there's a longer-term variation underway, it could manifest in all sorts of ways, not just in sunspot numbers, but in the structure of the heliospheric magnetic field, in the properties of the solar wind, in the frequency and intensity of extreme events. Some researchers have pointed to potential connections between solar dynamo variations and climate patterns on Earth, though the mechanisms are debated and the effects are small compared to other climate drivers. But the point is that the sun is a complex coupled system, and changes in one part can propagate to others in ways that aren't always obvious or immediate. There's also speculation, and I want to be clear that this is speculative and not established science, that some solar cycles might be predisposed to producing more extreme events than others based on the detailed structure of the magnetic field at solar maximum. The idea is that the configuration of the global dipole field, how cleanly it reverses polarity, how symmetric the field is between northern and southern hemispheres, might influence the probability of producing large complex active regions like AR4294. If the field reversal is messy, if there's residual complexity left over from the previous cycle, it might create conditions where unusually large and complex regions are more likely to emerge. This is frontier research, not something you'll find in textbooks, but it's the kind of thinking that happens when models fail to predict observations and researchers start looking for what might be missing. What all of this means for AR4294 is that we're dealing with uncertainty at multiple levels. We don't know if it will erupt, we don't know how powerful an eruption might be, and we don't know if there are aspects of its behavior that might surprise us precisely, because we're in uncharted territory with a late-cycle complex region appearing during a solar cycle that's already exceeded predictions. We're learning in real time, watching the sun do something we didn't fully expect, and trying to assess the threat level with imperfect information. It's not a comfortable position, but it's the reality of studying a star from the inside of its atmosphere, trying to predict behavior we can only partially observe in a system we only partially understand. And while we've been focused on AR4294 as a discrete threat, as a single active region that might or might not produce a major eruption, there's a broader and more sobering context we need to consider. Even if AR4294 rotates away quietly, even if this particular sunspot turns out to be a false alarm, the vulnerability it highlights doesn't go away, our infrastructure is fragile, our dependence on technology that's vulnerable to space weather continues to grow, and the Sun, indifferent to our concerns, will continue producing active regions and solar storms with a frequency and intensity we can estimate but not control. The question isn't whether there will be another major solar storm. The question is when, and whether we'll be ready. And to understand just how unprepared we might be, to grasp the full scale of what the Sun is capable of at its worst, we need to venture beyond Carrington, beyond even the most extreme events of recorded history, into territory where the only evidence comes from tree rings and ice cores, and the implications are almost too frightening to fully process. The numbers from modern impact studies should make anyone pause. A Carrington-class geomagnetic storm hitting Earth today would cause somewhere between $1 and $2 trillion in economic damage in the United States alone, with recovery taking years. That's not activist exaggeration or worst-case scenario modelling designed to scare people. That's the estimate from serious economic impact studies commissioned by government agencies and insurance companies trying to understand their exposure to space weather risk. To put that in perspective, Hurricane Katrina, one of the most destructive natural disasters in American history, caused roughly $125 billion in damage. A major solar storm would be an order of magnitude worse economically, and unlike a hurricane, which affects a region, a solar storm affects an entire hemisphere, potentially multiple continents simultaneously, depending on which side of Earth is facing the Sun when the coronal mass ejection arrives. There's no evacuating from a geomagnetic storm, there's no boarding up windows or moving to higher ground. You can only prepare your infrastructure and hope it's enough. But the economic numbers, as staggering as they are, don't capture the human reality of what a prolonged power grid failure would actually mean. Let's walk through what happens when the grid goes down, not for hours or days, but for weeks or months. We'll use a major city as our example, any major city with millions of people, because the effects would be similar anywhere. The first thing you notice when power goes out is obvious. Lights go dark, computers shut down, climate control stops. If it's winter, buildings start getting cold. If it's summer in a hot climate, they start getting dangerously hot. But you've experienced power outages before, so this doesn't seem catastrophic yet. You've got a flashlight, maybe a battery radio, you figure power will be back soon. But hours pass and it's not back. Night falls and the city is dark in a way cities never are anymore. No streetlights, no building lights, just darkness broken by scattered emergency lights running on batteries and generators where they exist. Day 2, you start noticing the cascading effects. Your phone battery is dead, and you can't recharge it because there's no power. Cell towers are running on backup generators where they have them, but those generators need fuel, and fuel pumps need power. Some stations have generators, but the fuel distribution system is already breaking down because the trucks that deliver fuel depend on GPS for routing and electronic systems for scheduling, and those systems are failing. So even places with generators start running out of fuel to run them. Communications begin to fragment. Without cell phones, without internet, people are isolated, dependent on battery radios if they have them, on word of mouth, on whatever information local authorities can broadcast. But even that's breaking down because emergency services are overwhelmed. Fire departments, police, hospitals, they're all trying to operate without the electronic coordination systems they depend on, rationing generator fuel, prioritizing emergencies, turning people away. Water is the next crisis. City water systems depend on electric pumps to move water through the distribution network and maintain pressure. Some pumping stations have generators, but again, fuel is the limitation. Within a couple of days, in many areas water pressure drops. Taps run dry or produce only a trickle, and even where water is still flowing, there's a more insidious problem: water treatment. Modern water treatment plants use electrically powered systems to filter and disinfect water. Without power, even if you get water out of your tap, you can't be sure it's safe to drink. Boil water advisories go out, but how do you boil water without power? Gas stoves work if you have gas, but if your building's water pressure is gone, you don't have water to boil. People start breaking into stores for bottled water. That runs out quickly. Authorities try to distribute emergency water supplies, but the logistics are overwhelming. Millions of people, each needing gallons of water per day just for drinking and basic hygiene, and no functioning distribution system to supply them. Sewage systems fail next. Toilets need water to flush and water pressure is gone. Even where people can manually flush by pouring water, the sewage systems often depend on electric pumps to move waste to treatment plants. Without power, those pumps stop and sewage backs up. Storm drains in many cities are interconnected with sewage systems, so you start getting sewage backing up into streets. In summer heat, with no power for sanitation, in a dense urban environment where millions of people are producing waste with nowhere for it to go, you're looking at a public health catastrophe unfolding. Disease vectors multiply. Cholera, typhoid, Diseases we think of as historical problems in developed nations suddenly become very real threats. Food is the next domino. Your refrigerator stopped working when the power went out. Day 1, the food is still cold. Day 2, it's warming up. Day 3, anything perishable is spoiling. Multiply that by every refrigerator and freezer in the city, every grocery store, every restaurant, every food warehouse. Millions of tons of food spoiling simultaneously, and even the non-perishable food in stores gets looted quickly because people are hungry and scared. Supply chains that bring food into cities break down completely without power for refrigeration, without functioning logistics systems to coordinate shipments, without fuel for the trucks that would transport supplies. Cities are consumption centers, not production centers. They depend absolutely on constant inflows of food from agricultural regions, and those inflows stop when the distribution system fails. Within a week, food scarcity becomes acute. People start leaving, evacuating not because authorities ordered it, but because staying is becoming untenable. But evacuating millions of people from a powerless city presents its own nightmare scenario. Cars need gasoline, and gas station pumps need power. Some people have enough fuel to leave, creating traffic jams of desperate evacuees on highways leading out of the city. Where are they going? If it's a widespread grid failure, nearby cities are in the same situation. Rural areas become destinations, but rural areas don't have infrastructure to support sudden influxes of urban refugees, and for those who can't leave, the elderly, the disabled, the poor without cars or resources, they're trapped in an increasingly unlivable environment, dependent on emergency services that are barely functioning. This is the 72-hour cascade, the recognition among emergency planners that once power goes out in a major urban area, you have roughly 3 days before the situation transitions from emergency to catastrophe. 3 days before the secondary effects of power loss start creating crises that are worse than the power loss itself. 3 days before the veneer of social order starts breaking down as people get desperate. And that's assuming the power outage is local, and help can come from unaffected areas. After Hurricane Katrina, despite all the failures in emergency response, help did eventually come because the rest of the country still had power, still had functioning logistics, still had resources to deploy. But if a Carrington-class geomagnetic storm takes down grids across multiple regions or an entire continent simultaneously, there's no external help coming because everyone is dealing with the same crisis at once. The cavalry isn't coming because the cavalry's stables are on fire too. Now let's talk about why the power goes out in the first place, and why getting it back on is so difficult. When a coronal mass ejection hits Earth's magnetosphere, it doesn't directly affect power lines or transformers. The effect is indirect but devastating. The CME's impact compresses and disturbs Earth's magnetic field, creating rapid variations in the field strength and orientation at the surface. Those rapid variations induce electric fields in the ground, and any long conductor like a power transmission line acts as an antenna for those fields, developing geomagnetically induced currents that flow into the power grid through grounded neutrals at substations. These are quasi-DC currents, very different from the AC power the grid is designed to handle. High-voltage transformers are particularly vulnerable. These massive pieces of equipment step voltage up to hundreds of thousands of volts for long-distance transmission and then step it back down for distribution. They're carefully designed to handle AC power at specific frequencies, and they're not designed to handle DC currents flowing through their windings. When GC flows through a transformer, it causes the magnetic core to saturate asymmetrically, shifting the operating point on the magnetization curve. That creates harmonics in the AC waveform, generates excessive heat, and can cause insulation breakdown. During the 1989 Quebec blackout, GIC levels reached hundreds of amperes in some transformers. They're designed to handle zero DC current, so hundreds of amperes is a massive stress that pushed equipment beyond its design limits. Some transformers shut down protectively, others sustained damage. The grid collapsed in cascading fashion as overloaded components tripped offline and the load redistributed to other components that then also overloaded and tripped. The blackout lasted 9 hours because the damage was limited, and utility crews could restore the system by bringing components back online in controlled sequence. But now imagine the geomagnetic storm is 10 times stronger, like Carrington was. Imagine GIC levels not in hundreds of amperes but thousands. Imagine not just protective shutdowns, but permanent transformer failures, the internal windings melting from the heat, the insulation breaking down catastrophically, transformers catching fire or exploding from the stress. That's what happened to some transformers in 1989, and that was from a much weaker storm than Carrington. The nightmare scenario isn't just that the grid shuts down, it's that the grid sustains permanent damage to critical components that take years to replace. Extra high voltage transformers, the really big ones that form the backbone of the transmission network, are not commodity items. They're custom engineered for specific locations, Built to order by a handful of specialized manufacturers, mostly overseas, a single large power transformer can weigh hundreds of tons, cost millions of dollars, and have a manufacturing lead time measured in years from order to delivery. They're transported by specialized heavy haul equipment because they're too large for normal freight. The United States has virtually no domestic manufacturing capacity for these transformers. We import them. And in a scenario where a Carrington-class storm affects not just the US but also Europe and Asia simultaneously, everyone would be trying to order replacement transformers at the same time from manufacturers who might themselves be affected by power grid issues in their own countries. The supply bottleneck would be catastrophic. Some estimates suggest that if a Carrington-class storm destroyed or damaged hundreds of these extra-high voltage transformers across North America, full grid restoration could take years because of the replacement pipeline, years without full power. Not everywhere simultaneously. Utilities would prioritize restoration and build back segment by segment, but large areas could be without power for months or longer. And remember the 72-hour cascade. Now extend it to months. Cities become unlivable. Population movements become migrations. The economic damage isn't just from the blackout, but from the complete disruption of normal economic activity for an extended period. Manufacturing stops. Agriculture struggles without modern equipment. The financial system seizes up without electronic trading and banking. It's not an exaggeration to say that a severe enough solar storm could set modern technological civilization back decades, at least temporarily, by destroying the infrastructure that enables everything else. And power grids aren't the only vulnerable infrastructure. Satellites are exquisitely vulnerable to the radiation and plasma environment during major solar storms. The energetic particles accelerated by solar eruptions and geomagnetic storms can penetrate spacecraft shielding and damage sensitive electronics through single-event effects, where a single high-energy particle strikes a critical component and causes a bit flip or latch up in the electronics. Minor events cause temporary glitches. Major events can permanently damage or destroy satellites. During the 1989 storm, several satellites experienced anomalies. During the Halloween storms of 2003, more than half of all Earth-orbiting satellites reported problems, and several were permanently lost. Scale that up to Carrington intensity, and the satellite industry faces potential catastrophic losses. GPS satellites, communications satellites, weather satellites, Earth observation satellites, the entire orbital infrastructure that modern civilization depends on for everything from navigation to banking to weather forecasting could be severely damaged. GPS deserves special attention because the dependence runs deeper than most people realize. Yes, GPS tells your phone where you are and helps you navigate, but GPS is also the timing backbone for critical infrastructure. Cell phone networks use GPS timing to synchronize towers. The power grid uses GPS timestamps for synchronized measurements across the network. Financial markets use GPS time for transaction timestamping. If GPS satellites fail or their signals become unreliable, it's not just navigation that breaks. It's precise timing for systems that depend on nanosecond-level synchronization across vast distances. We built critical infrastructure on the assumption that GPS would always be available, and if that assumption breaks, secondary failures cascade through systems that don't seem GPS-dependent at first glance. The aviation industry has modeled solar storm impacts, and the numbers are sobering. During major solar storms, radiation levels at airline cruising altitudes increase significantly, especially on polar routes where Earth's magnetic field provides less shielding. The radiation dose rate can reach levels where passenger and crew exposure becomes a health concern, particularly for pregnant passengers and crew. Airlines respond by rerouting flights to lower latitudes, but that adds flight time, increases fuel consumption, and reduces available routes. During the Halloween storms of 2003, airlines cancelled or rerouted dozens of flights. Scale that to Carrington intensity, potentially sustained over multiple days, and you're looking at widespread flight cancellations, massive economic losses for the airline industry, and significant disruptions to global travel and cargo transport. And that's assuming the GPS and communication systems planes depend on are still functional, which they might not be. So when we watch AR4294 and worry about whether it will erupt, we're not just worried about a scientific curiosity or a beautiful aurora display. We're worried about the potential disruption or destruction of infrastructure that billions of people depend on for survival in the modern world. We've built a civilization on electrical power and electronic communications and satellite services, and we've built it in the shadow of a star that has demonstrated, repeatedly throughout history, that it can reach out and break those systems when it stirs itself to real fury. And Carrington is not even the worst the sun can do. History, written in tree rings and ice cores, tells us there's another level beyond Carrington. Events so powerful they dwarf even the largest storms of the instrumental era. Events that modern civilization has never experienced, and that brings us to the genuinely terrifying part of this story. Because the evidence is undeniable that these extreme events are real, and we have no idea when the next one is coming. In the mid-2000s, a Japanese physicist named Miyake was studying tree ring data looking for information about past cosmic ray levels. Tree rings are remarkable historical archives. Each year, trees add a new growth ring, and the chemistry of that wood preserves information about environmental conditions when it grew. One isotope that gets preserved is carbon-14, a radioactive form of carbon created when cosmic rays strike nitrogen in the upper atmosphere. The carbon-14 production rate varies with cosmic ray intensity, which is modulated by solar activity and geomagnetic field strength. So by measuring carbon-14 levels in tree rings, you can reconstruct a history of cosmic ray exposure going back centuries or millennia, much further back than any instrumental record. Miyake was analysing high-resolution carbon-14 data from ancient cedars in Japan when she found something that shouldn't have been there, a massive spike in carbon-14 in the rings from 724 CE and 775 CE. The increase was about 12 parts per thousand over background. A huge anomaly that showed up in trees from multiple locations, ruling out local contamination. The immediate question was what could cause such a spike. Carbon-14 is produced by cosmic rays, so something must have dramatically increased the cosmic ray flux reaching Earth's atmosphere in 774 or 775. A supernova? Possible, but there were no astronomical records from that period describing a bright new star appearing in the sky, which you'd expect from a nearby supernova. A gamma-ray burst? Even less likely, because the energy requirements and the probability of one happening so recently and close enough to affect Earth are astronomically small. That left solar activity. A solar flare or coronal mass ejection releases massive amounts of high-energy particles, solar energetic particles that can reach Earth in minutes to hours and bombard the atmosphere, creating carbon-14 through the same nuclear reactions that cosmic rays cause. But here's the problem. The magnitude of the 774 event based on the carbon-14 spike was enormous. The estimates suggested a solar energetic particle event, assuming solar origin, at least 10 times larger than the largest solar storm in modern observation, and more likely 20 times larger or more. It was unprecedented. Other researchers started looking for corroborating evidence and found it. Ice core records from Greenland and Antarctica showed spikes in beryllium-10 and chlorine-36, other cosmogenic isotopes produced by energetic particles at the same time period. The event was global and it was massive. And then, as researchers looked more carefully at the high-resolution data, they found another event in 993 CE with similar characteristics. Two extreme solar events, or whatever they were, separated by roughly 2 centuries. These became known as Miyake events, and they've generated an enormous amount of research and debate because they represent something we've never witnessed directly, but can't ignore because the evidence is sitting there in tree rings and ice cores, undeniable proof that these things happen. The debate centers on what exactly caused them. The solar flare explanation has support because it's the most plausible mechanism, and we know the Sun is capable of large particle events. But the magnitude is the problem. The largest solar energetic particle event in modern observation was in 1859, associated with the Carrington Event, and even that pales in comparison to the 774 event by a factor of 10 or more. For a solar event to produce the observed carbon-14 spike, it would have to be not just a large flare but an enormous one, perhaps an X100 or X500 class event, categories we've never observed because they're so far beyond anything in the modern record. And it would have to launch particles with the right energy spectrum and intensity to reach Earth's atmosphere in sufficient numbers to create the isotope spike. It's possible, the physics allows it, but it pushes the boundaries of what we think solar flares can do. Alternative explanations have been proposed. Maybe it was a series of large solar events clustered in time rather than a single monster event. Maybe the Sun was in an unusual activity state that allowed for exceptional particle production. Some researchers have even suggested exotic scenarios like a passing comet hitting the Sun or interactions with the Sun's global magnetic field during a particularly chaotic polarity reversal. None of these alternatives are particularly satisfying either because they require special circumstances that we have no other evidence for. The most straightforward explanation remains a solar superflare, but accepting that means accepting that the Sun can do something far more violent than anything we've prepared for or witnessed in the modern era. And here's what should genuinely terrify you. If Miyake events are solar in origin, and the statistical analysis of the limited sample suggests they happen roughly every 1,000 years on average, then they're rare but not impossibly rare. We're talking about geological timescales, but we're not talking about million-year events. They happen. The last confirmed one was over 1,000 years ago. Are we overdue? That's not how statistics work. Each event is independent and past occurrences don't predict future ones. But it highlights that we're living under a star that has demonstrated it can produce particle storms 20 times stronger than Carrington, and we have no way to predict when the next one will happen because we don't fully understand what causes them in the first place. Now let's think about what a Miyake-class event would do to modern civilization. If Carrington was bad, threatening power grids and satellites with a G5 geomagnetic storm, a Miyake event would be incomprehensibly worse. The energetic particle flux would be so intense that it wouldn't just threaten satellites, it would sterilize Earth orbit. Spacecraft electronics would be fried by the radiation storm. Solar panels would degrade instantly from particle bombardment. Communication and navigation systems would fail across the entire satellite fleet. Every satellite in low Earth orbit, every GPS satellite in medium Earth orbit, every communications satellite in geostationary orbit, all of it potentially damaged beyond repair. We'd lose orbital infrastructure that took decades to build in a matter of hours. The radiation exposure at aviation altitudes would be acute enough to force grounding of all flights during the storm, not out of abundance of caution, but because crew and passengers would be exposed to radiation doses equivalent to multiple chest X-rays per hour of flight at cruise altitude. The FAA and international aviation authorities have dose limits for aircrew, and a Miyake-class storm would blow through those limits in minutes. Polar routes would be completely untenable. Even mid-latitude flights would carry serious radiation risk. Global aviation would shut down for the duration of the storm, which could be days. On the ground, the geomagnetic effects would be Carrington on steroids. Geomagnetically induced currents wouldn't just stress power grids, they'd destroy them. Transformers wouldn't just overheat, they'd catastrophically fail in numbers that would make grid restoration not a matter of months but years. And it wouldn't just be high-voltage transmission, it would cascade down to distribution systems, to substations, to equipment at every level of the grid infrastructure. The damage would be so widespread that utilities would be looking at essentially rebuilding the grid from scratch in many areas. That's not a recovery operation, that's reconstruction. And while the grid is down, everything else fails. Water, sewage, food distribution, communications, all the cascading failures we talked about before, but sustained for years instead of weeks. The economic impact would be measured not in trillions, but in the fundamental disruption of the global economy. Modern economics depends on instant communication, reliable power, functioning logistics. Take those away for years and you're not talking about an economic recession. You're talking about economic collapse, the breakdown of global trade networks, the fragmentation of the world economy into regional economies that can function without electronic infrastructure. It's not the end of civilization. Humans are resilient and we'd adapt. But it would be the end of modern technological civilization as we know it, at least temporarily. We'd be forced back to lower technology levels out of necessity until we could rebuild the infrastructure that makes modern life possible. And here's the most unsettling part. We don't know how to predict these events. We don't know what warning signs to look for because we've never observed one. The Carrington event had a large sunspot, but Miyake events, if they're solar, might not follow the same patterns. They might be associated with particularly complex active regions like AR4294, or they might emerge from solar conditions we haven't recognized as dangerous because we've never seen what comes next. We're in the position of knowing these events exist, knowing they're devastating, knowing they happen on timescales that could be centuries or could be tomorrow, and having absolutely no predictive capability. We can monitor the sun, we can watch for unusual behavior, but we can't say with any confidence that we'd recognize a Miyake-class event building before it happened. The tree ring evidence tells us the 774 and 993 events happened. The physics tells us they were almost certainly solar in origin. The magnitude tells us they were far beyond anything in modern observation. And the frequency tells us they're rare but not impossible. We're living under a star capable of producing these monster events. And we've built a civilization that would be devastated if one occurred today. That's the Miyake shadow, darker and longer than even Carrington's. The knowledge that the sun's full fury is something we've read about in isotopes but never experienced. And the uncomfortable recognition that our luck could run out at any time. And while Miyake events represent the extreme tail of the solar threat distribution, the everyday reality is that we're constantly in the sun's crosshairs, constantly at risk from events that are far more common and far more likely than Miyake-class superstorms. And right now, one of those more common but still dangerous threats is pointed directly at us, rotating across the solar disk, and we're watching it in real time, wondering if this is the rotation when our luck runs out. As you're watching this, AR4294 is rotating. The sun's surface doesn't stand still. It churns with convective motion and rotates on its axis with a period of roughly 27 days as viewed from Earth. Slightly longer than the sun's true rotation period because Earth is also orbiting the sun in the same direction, so we're chasing the rotation a bit. Every hour that passes, AR4294 moves about half a degree across the solar disk as viewed from Earth. That doesn't sound like much, but over the course of a day it's 15 degrees, and in just a few days, it will have rotated from its current near-central position past the western limb, where it will no longer be geoeffective, where any eruption would be directed away from Earth into empty space. Right now, we're in the critical window. Solar physicists talk about the geoeffective zone, the portion of the solar disk where an active region is close enough to central meridian that any eruption will be directed at or near Earth. Roughly speaking, that's within about 45 degrees of central meridian, a 90-degree band centered on the Earth-Sun line. AR4294 is in that zone now, and depending on exactly when you're watching this, it's either approaching the most dangerous angle at it or just past it. Every hour that it remains in this window without erupting is another hour of stored energy, another hour of accumulated stress, and another hour closer to when the geometry will save us simply by rotating the threat away from Earth's direction. The monitoring is constant and intense. The Solar Dynamics Observatory, NASA's spacecraft watching the Sun in multiple wavelengths continuously, captures full-disk images every few seconds. Those images are processed in near real-time and made available to forecasters and researchers around the world. Every brightening in AR4294, every change in magnetic field structure, every hint of instability gets analysed for signs that an eruption might be imminent. Ground-based solar observatories add their data, particularly magnetogram measurements that map the magnetic field strength and polarity across the active region. The data streams are enormous, terabytes of information every day, and automated systems flag anomalies, but ultimately humans are watching, experts who have spent careers studying solar activity and who develop an intuition for what normal looks like and what dangerous looks like. The forecasts are updated multiple times per day. The Space Weather Prediction Center, NOAA's operational space weather office in Boulder, Colorado, issues Outlook products that assess the likelihood of solar flares from each numbered active region. For AR4294, those probabilities have been elevated throughout its Earth-facing passage because of its size and magnetic complexity. As of the latest forecast, and I'm deliberately not giving a specific date because this could be watched days or weeks after recording, the probabilities are high enough that forecasters are explicitly calling out AR4294 as a threat. The exact numbers vary day to day as the region evolves, but we're talking about a significant chance of M-class flares and a non-trivial chance of X-class flares while the region remains geoeffective. Those aren't certainties. They're probabilities based on historical behavior of similar regions. But they're high enough that satellite operators are paying attention, that power grid operators are aware, that anyone whose systems are vulnerable to space weather is on alert. And yet, the eruption everyone is expecting hasn't happened. AR4294 has produced some activity, minor flares that don't make headlines, but nothing proportional to its size and complexity. The quiet continues, and with each passing day the tension increases because the window is closing. In a handful of days, maybe a week depending on when you're watching this, AR4294 will rotate beyond the western limb and disappear from Earth's view. It will still exist, still be just as magnetically complex and energetic, but it will be on the far side of the Sun where we can't see it directly, and where any eruption would be directed away from Earth. We'll lose visual monitoring capability. We'll only know about far-side activity through indirect means, like helioseismic measurements that detect acoustic waves from solar flares propagating through the Sun's interior, or from spacecraft positioned away from the Earth-Sun line that can see the far side. But the threat to Earth will be gone for that rotation, unless it erupts before then, unless the stress finally exceeds what the magnetic field can hold and the reconnection cascade begins while AR4294 is still facing us. Then we get the full impact, the X-ray and particle radiation arriving in minutes, the coronal mass ejection arriving in days, and the test of whether our infrastructure can handle what's coming. This is the waiting game that's been playing out for the past week or more. This uncertainty about whether AR4294 will fire while aimed at us, or whether we'll dodge this particular bullet simply by virtue of timing. There's also the possibility, less discussed but worth mentioning, that AR4294 erupts just after rotating past the limb, when it's no longer fully visible but still close enough to the edge that a coronal mass ejection might have a glancing trajectory toward Earth. CMEs don't always launch radially from the Sun's surface. They can be deflected by the Sun's large-scale magnetic field structure, and eruptions near the limb can sometimes produce CMEs that curve around and end up partially Earth-directed even though the source region wasn't centrally located. So even after AR4294 rotates out of direct view, there's a lingering tail risk for a few more days until it's far enough around the limb that the geometry truly rules out Earth impact. For those of us watching, for the solar physics community and space weather forecasters and anyone who understands what's at stake, this period has been a masterclass in uncertainty management. We know the threat is real, we know the potential consequences are severe, we know we're in the time window when it matters most. But we don't know if it will actually happen. We can't force the Sun to follow our models or our expectations. We can only watch and wait and prepare for the possibility that this could be the event we've been concerned about for decades, the major solar storm hitting modern infrastructure directly and testing whether all the preparations and hardening efforts are sufficient. And the preparations have been made to an extent. Power grid operators in regions likely to be affected by a major geomagnetic storm have procedures in place to reduce grid loading, to disconnect vulnerable transformers, to operate in configurations that minimize exposure to geomagnetically induced currents. Satellite operators can put spacecraft into safe mode, turning off non-essential systems and orienting solar panels and antennas to reduce risk. Airlines can reroute flights away from polar regions where radiation exposure would be highest, but these are mitigation measures, not solutions. They reduce risk, they don't eliminate it, and they come with costs. Reducing grid loading means cutting power to some customers. Safe mode means satellites aren't doing their jobs. Rerouting flights means delays and increased fuel costs. So there's a balance between preparing for a threat that might not materialize and maintaining normal operations. Forecasters try to thread that needle by providing probabilistic guidance, but ultimately, decision-makers have to choose based on incomplete information. If AR4294 does erupt with a major flare and coronal mass ejection while aimed at Earth, we'll have roughly 8 minutes of warning from the flare itself, the time it takes light to travel from Sun to Earth. Space weather monitoring spacecraft will detect the X-ray spike and immediately alert ground stations. Within minutes, forecasters will assess the flare's magnitude and issue alerts. That's enough time for satellite operators to receive the warnings and take protective actions, enough time for airlines to be notified, enough time for forecasts to be updated. But it's not enough time to fundamentally change infrastructure vulnerability. 8 minutes doesn't let you shut down a national power grid, or evacuate cities, or recall aircraft already in flight over vulnerable routes. The coronal mass ejection, if the eruption produces one, takes longer to arrive, typically 1 to 3 days depending on its speed. That gives much more warning time, and forecasters will track the CME as it crosses the space between Sun and Earth using spacecraft like SOHO that can image the Sun's corona and see the plasma cloud expanding outward. The arrival time can be estimated, though with uncertainty of several hours, and the likely geomagnetic impact can be assessed based on the CME's speed and magnetic field orientation. Strong impacts require not just a fast dense CME but also one with a southward magnetic field component that can efficiently couple with Earth's northward field. If the CME's field is northward, the interaction is much weaker and the geomagnetic effects are reduced. But we don't know the CME's magnetic orientation until it arrives at the L1 point, about 1 million miles upstream of Earth, where monitoring spacecraft can measure it directly. That gives about 30 to 60 minutes of final warning before the CME hits Earth's magnetosphere. Not a lot of time, but enough to issue the final alerts and for operators to take last-minute protective measures. So the timeline of a major space weather event from AR4294, if it happens, would look something like this. Flare erupts, 8-minute light travel time, X-ray flux hits Earth causing immediate radio blackouts and satellite effects, alerts go out within minutes, coronal mass ejection launches and becomes visible to coronagraphs, transit time 1 to 3 days, updates issued continuously as CME crosses space. Final warning when CME reaches L1 point, 30 to 60 minutes later the CME hits Earth's magnetosphere, geomagnetic storm begins, effects on power grids and satellites over hours to days depending on storm duration. Each phase has specific threats and required responses, and the whole sequence is what forecasters and operators are prepared to handle if AR4294 stops being quiet and starts being violent. But right now, the quiet continues, the rotation proceeds, and the window slowly closes. Every day without eruption is a day closer to safety. To AR4294 rotating away from Earth-facing geometry and becoming someone else's problem for the next 2 weeks until it rotates back into view. If you're watching this a week or more after recording, AR4294 might already be past the limb, the immediate threat over, or it might have erupted and you're watching in the aftermath, or it might still be there, still quiet, still threatening, and the waiting continues. This is the reality of space weather forecasting, living with uncertainty, making decisions with incomplete information, preparing for threats that might not materialize while knowing that someday one of these threats will materialize and we'll find out if we were prepared enough. And as we watch this drama unfold on the Sun 93 million miles away, as we wonder whether AR4294 will erupt or rotate away peacefully, it's worth stepping back and asking what this moment teaches us about our place in the universe, about the fragility of the technological civilization we've built, and about our relationship with the star that makes all life on Earth possible, while also threatening the infrastructure that supports modern life. Because there's a deeper story here beyond the immediate threat, a story about humanity's long dance with the sun, and what it means to live at the mercy of forces we can observe but not control. There's a certain hubris in modern technological civilization, a quiet assumption that we've mastered our environment, that we've insulated ourselves from nature's whims through engineering and science. We build cities that ignore geography, climate-controlled spaces where it's always comfortable regardless of the weather outside. We've extended our presence into space with satellites and space stations. We've connected the entire planet with instantaneous communications. We've built systems so complex and interconnected that they seem almost invulnerable by virtue of their sophistication. And then the sun reminds us that we're still living in its atmosphere, still dependent on its light and warmth, still vulnerable to its moods, and all our sophistication is built on infrastructure that can be damaged or destroyed by magnetic storms launched from 93 million miles away. It's a humbling realization, and one we don't like to dwell on because it contradicts the narrative of technological mastery. But the truth is that humanity has always lived at the sun's mercy. For billions of years before humans existed, life on Earth was shaped entirely by solar radiation, by the energy driving photosynthesis and weather and climate. Our ancestors worshipped the sun as a deity, which makes sense when you realize that everything they depended on, the warmth, the light, the seasons, the crops, all came from that burning disk in the sky. They didn't understand the physics, but they understood the dependence. Modern civilization understands the physics beautifully. We know the sun is a star, a ball of hydrogen fusing into helium at 15 million degrees in its core, generating energy that radiates outward and takes 100,000 years to random walk from core to surface before finally escaping as the light that reaches Earth 8 minutes later. We understand solar physics in remarkable detail, but understanding doesn't grant control. We can't turn the sun down when it gets active. We can't prevent solar flares or coronal mass ejections. We can only watch and try to protect ourselves and hope our preparations are sufficient. AR4294. Whether it erupts during this rotation or not, whether it produces a major Earth-directed storm or fades away peacefully, has served as a reminder of that fundamental vulnerability. For a week or more, the space weather community has been on edge, watching a sunspot that has all the characteristics of a major threat, wondering if this will be the event that tests our infrastructure in ways it hasn't been tested before. The tension comes from the contrast between the sophistication of our monitoring, the satellites and observatories and models that let us track every detail of AR4294's evolution, and the ultimate powerlessness we have to do anything but prepare and hope. We're spectators to processes beyond our control, and while we've learned an enormous amount about how the sun works, that knowledge hasn't fundamentally changed our position. We're still living on a planet orbiting a variable star, still dependent on that star, remaining relatively well-behaved, and still vulnerable when it decides to unleash its full fury. The lesson from AR4294, and from Carrington before it, and from the Miyake events in the tree ring record, is that space weather is not a hypothetical threat. It's a real, recurring, infrastructure-level risk that we've been lucky to avoid in its extreme forms during the modern technological era. We've had close calls: the 1989 Quebec blackout, the Halloween storms of 2003, the May 2024 event that triggered strong auroral displays and satellite issues. Each of these was a warning, a preview of what could happen if the storm was larger, or the impact more direct, or the infrastructure less prepared, and each time we've learned something and hopefully improved our resilience a little. But there's a fundamental limit to how much you can harden infrastructure against geomagnetically induced currents without massive investment, and the economics of power grid operation don't incentivize utilities to spend billions on protection against rare events. The regulatory framework in most countries doesn't require it, so while awareness has increased and some hardening efforts have been made, the vulnerability remains. What would it take to truly protect critical infrastructure against solar storms? For power grids, you'd need to install blocking devices at substations to prevent GIC from flowing into transformers, or design transformers that can tolerate DC currents, or reduce the interconnection distances so that grid segments are less vulnerable to large-scale GIC. All of these are technically feasible but expensive, and the costs run into the hundreds of billions of dollars for continental-scale grids. For satellites, you'd need more radiation hardening, which adds weight and cost and reduces performance. For GPS and communications, you'd need redundancy, backup systems that use different technologies, not vulnerable to the same threats. It's all possible. But it requires sustained investment and political will, and a recognition that space weather is a priority risk worth spending serious resources to mitigate. And frankly, that recognition isn't there yet in most places. Space weather competes for attention and resources with more immediate and visible threats like hurricanes and floods and cyber attacks, and it usually loses because it's abstract and infrequent, and the last major event was over a century and a half ago. But maybe AR4294, even if it doesn't erupt, serves a purpose by raising awareness. Every time a major active region appears and gets media attention, every time forecasters issue warnings and people talk about solar storms, it plants a seed of understanding that this is real, that the sun is not just a benign light in the sky, but a dynamic and occasionally dangerous neighbour. And maybe over time, as those seeds accumulate, as the message penetrates into policy and investment decisions, we'll build the resilience we need to weather the next Carrington event or even survive a Miyake-class storm without civilization-ending consequences. It's possible. We have the technology. We have the knowledge. What we need is the collective will to prioritise long-term resilience over short-term cost optimization. In the meantime, we watch, we monitor, we forecast, and we hope. Right now, somewhere in the world, a space weather forecaster is looking at the latest images of AR4294, checking the magnetic field measurements, assessing whether there are signs of impending eruption. Satellite operators are keeping an eye on the forecasts, ready to safe their spacecraft if warnings escalate. Power grid operators are aware of the threat and prepared to take protective measures if needed. And millions of people are going about their daily lives, mostly unaware that there's a sunspot 10 times wider than Earth pointed at us, mostly unconcerned because the sun has been shining reliably every day of their lives, and there's no reason to think tomorrow will be different. That disconnect between the informed concern of the experts and the casual indifference of the public is natural. We can't all be worried about every low probability, high consequence risk all the time. That's not a functional way to live. But it does mean that when the low probability event finally occurs, it comes as a shock to most people, and the response is reactive rather than proactive. AR4294 will rotate away soon if it hasn't already. The immediate threat will pass, and life will continue normally, and most people will never know they were in the crosshairs of one of the largest sunspots of this solar cycle during its Earth-facing passage. But the sun's cycle continues. New active regions will emerge. Some will be large and complex and threatening, some will erupt, and someday, maybe this year, maybe next decade, maybe next century, one of those eruptions will be powerful and well-aimed, and we'll experience a major solar storm that tests our infrastructure for real. When that happens, the outcome will depend on how well we've prepared, how robust our systems are, how quickly we can respond. And the time to prepare is not after the event but before, in the long quiet periods between storms when investment in resilience seems like unnecessary expense because nothing bad is currently happening. That's the final lesson from AR4294. The threat is real, the vulnerability is real, the consequences of a direct hit from a major solar storm are severe. But we're not helpless. We can monitor, we can forecast, we can build resilience, we can reduce the vulnerability of critical infrastructure, we can plan for response and recovery, we can educate the public and policymakers about the reality of space weather risk. All of these are things we should be doing, and to varying degrees, we are. But more is needed, more investment, more attention, more recognition that we live on a planet orbiting a star that is mostly benign but occasionally violent, and our technological civilization, for all its sophistication, remains vulnerable to that violence in ways we haven't fully addressed. As AR4294 rotates across the sun's face, it's worth remembering that this is not the last time we'll face a threat like this. The sun's cycle continues. The dance between Earth and its star continues. And our responsibility is to build a civilization resilient enough to survive not just the threats we've seen, but the threats we know are possible, even if we haven't witnessed them yet. That's the challenge space weather presents, and it's one we can't afford to ignore simply because the sky's currently clear and the sun is currently shining and nothing bad is happening right now. Because eventually something will happen, and when it does, we'll need to have been ready long before the first warning arrives.